The 1954 paper of Professor Yang and Robert Mills is the most important theoretical paper for the second half of the 20th century. By now, their non-abelian gauge theory has permeated many branches of physics and is expected to be even more important for this century. We would like to speculate in some detail about how this Yang-Mills theory can become more important. Let me emphasize this is speculation. When I was a first-year graduate student, Professor Yang came to Harvard to give a colloquium on this Yang-Mills non-abelian gauge theory. This morning, Professor Yang told me that this was the first time that he had given a colloquium on this theory. Therefore, I must be one of the first persons who has heard about this Yang-Mills theory. I have to admit, however, that I did not understand much from Professor Yang's talk. This was also the first time I met Professor Yang, and he has since influenced greatly my research from that time on. I would try to present now a new scenario. But as I already emphasized, this is speculation. In particle physics, in particular, there are many consequences of the Yang-Mills non-abelian gauge theory. One of the most important ones is that the Yang-Mills theory has led to the standard model of Glashow, Salam, Weinberg, Iliopolis, Liani, and others. In this particular theory, the Yang-Mills gauge group is U1 cross SU2 cross SU3. We have just heard a detailed discussion of the SU3 part of the theory. What I would like to discuss today is to take together Yang-Mills gauge theory and the Higgs boson. In 2012, officially announced on July 4, almost 3 years ago, the Higgs boson was discovered. The Higgs boson was originally proposed by Engler, Braut, Higgs, Gronik, Hagen, and Kibble. What had happened in 2012 was that the Atlas collaboration and the CMSS collaboration has experimentally discovered the Higgs boson using the Large Hadron Collider of Tsun. The discovery of Higgs boson was made mainly through the Higgs decay mode of Higgs going to gamma gamma. One of the main reasons why this particular decay mode is so important is because of the lack of background for this process. It does not have a much of a background. This Higgs boson is the first spin zero elementary particle ever observed. Therefore, it's not only a new particle discovered, but possibly a new class of particle discovered. Having trouble finding the button. Due to the importance of this Higgs gamma gamma, the theoretical calculation of the decay deserves a closer look. The reason, a particular reason for looking at that once more was the following. Since the photon has no mass, it has no direct coupling to the Higgs boson. Therefore, this decay, Higgs goes to gamma gamma, has to go through one loop of some heavy particle. But this one loop decay of Higgs go to gamma gamma has to be finite, because if it were not finite, there's no way to renormalize it, since the direct coupling is absent. This means that the Higgs to gamma gamma decay must be possible to be calculated in a completely straightforward manner without using complicated tricks. Yet, the existing calculation at that time, in 2011, 4 years ago, used the dimensional regularization and ghosts and so on. Therefore, we decided to recalculate this decay mode in this straightforward manner. This was done in collaboration with Raymond Gessman in 2011. Last year, this calculation was carried out independently by Christopher and Todorov. We did our calculation carefully to avoid possible complications, but we still use Feynman diagrams. Christopher and Todorov are very good field theorists, and they know that Feynman diagrams are not always reliable. So they did their calculation avoiding Feynman diagrams. Their calculation is about as rigorous as anything can be in physics. We of course, got the same result. The result was that the Higgs to gamma gamma, as measured by Atlas collaboration and by the CMS collaboration, divided by the Higgs to gamma gamma theory, is about 3. This number 3 has changed quite a bit. It started out about 3.5, and CMS revised that data, and then it went down to 3 and went down to about 2.5. Now they revised their data again, and now back to about 3. So I say roughly 3. Such a major discrepancy between theory and experiment must imply some new physics. What we would like to talk about today is to speculate what the new physics can be. The theoretical calculation of Higgs gamma to gamma gamma go through a loop. And for particles in the standard model, the heavy particles are top and W. They have to be charged, so these do not do anything. It is with these two type of loops that the result gives a ratio of 3, as I just showed. So the discrepancy between experiment and theory must mean there are some additional particles, X. X has to be heavy in order to couple to a Higgs particle. But what can this X be? We argue that this additional heavy particle X is likely to be a spin 0 particle. Why? If it was spin 1, that's additional Yang-Mills gauge particle, and this will change the theory greatly. That's unlikely. If it's spin 1/2, then it's likely to be a 4th generation particle. There have been extensive efforts to look for 4th generation, and nothing has come up. That's why we believe it's a spin 0 particle, these additional X's. Now, if we introduce a spin 0 particle to the loop, a 1 is not enough. The contribution depends on the mass of the particle, but even if you take the maximum contribution, it's not enough to do much. So we take at least 5 spin 0 particles to do it. So we have to introduce at least 5 particles. So therefore, we believe the additional particles are likely to be scalar quarks and scalar leptons. If that's the case, then this suggests Fermi-Boson symmetry. Of course, scalar quarks are just the same as quarks except for spin, and scalar leptons are just the same as leptons except for spin, and therefore scalar quarks have color and so on, and scalar leptons have lepton numbers. Therefore, by introducing Fermi-Boson symmetry, we start with the Yang-Mills gauge theory that led to a standard model, and then we try to get to a new scenario by modifying the standard model. So what does the new scenario look like? We would like to discuss our preliminary results. What can we say about the scenario? Of course, it has to be a Yang-Mills non-abelian gauge particle. We don't want to change the gauge group, therefore it's still U1 cross SU2 cross SU3. Since the 4th generation particles have never been seen, we say there are 3 generations of particles. Right now, there are 3 generations of quarks and leptons. So for this, we want to have 3 generations of quarks, leptons, scalar quarks, and scalar leptons. There's just one Higgs boson. We'll come back to it on the next next one. And the scalar quarks and the charged scalar leptons are not long-lived. We also assume that in the interaction, the terms are all of dimension 4, except for the Higgs mass term. What this means is roughly that there are no soft terms. This is copied from quantum electrodynamics. Let me go through the reason for having this, the point 4 and 5. Point 4, the Higgs boson found in 3 years ago, coupled to top, bottom, W, and Z. This is the experimental result from Atlas, CMS, CDF, and D0. I should add that in making up this story now, we try to take into account whatever experimental information we have. B, no second Higgs boson has been seen up to about 700 or 800 GeV. And for 0.5, no new stable or long-lived charged particle had been seen by Atlas or CMS collaboration. Professor Yang has emphasized symmetry dictates interaction. So our central question now is, what does the fermion-boson symmetry imply about the interaction? Of course, we realize the fermion-boson symmetry is not a local symmetry. It is not a continuous symmetry, but nevertheless, it's a symmetry should imply something about interactions. For that, we again look at Professor Yang's work to get some indication. Professor Yang said, I do not believe that any of these greater Lie algebra has the intrinsic and fundamental beauties of the Lie algebra and Lie groups, not as yet. So in this new scenario I'm trying to present, there's only one Higgs doublet, therefore it cannot be any greater Lie algebra. And furthermore, since there's only one Higgs doublet, the Higgs doublet cannot have a fermionic partner because there'll be anomaly cancellation. So this fermion-boson symmetry is not complete in the sense that every particle has a partner. So here's the list. The U tilde are the scalar particle, and so on. In more detail, with isospin listed, the two left elements are isospin doublets, while the right elements are isospin singlets, just as we usually do. It should be emphasized that UL tilde and UR tilde are two independent scalar particles, complete different masses and so on. Now, what do we do with this? Contributions from fermionic groups and bosonic groups often have opposite signs because there's a minus sign for every fermionic group. They have opposite sign, but in order for them to cancel, the value have to be the same. So the cancellation divergences often leads to relation between the parameters, in particular, the particle masses. I have given here a list of all the particle masses except the Higgs boson, which is at 125 GeV. In this list, we emphasize the heaviest, by far the heaviest one, is the top quark. The following fact has impressed us very much. The top quark was first observed 20 years ago by the CTF collaboration and D0 collaboration in Fermilab. No heavier elementary particle has been seen since then. It has remained the heaviest particle for 20 years. In fact, there have been a number of celebrations for the 20th year anniversary of the discovery of the top quark this year. So we would like to believe that top quark, at least temporarily believe, that the top quark is the heaviest elementary particle, that there's no elementary particle heavier than top quark, until we're shown otherwise. Note that in these 20 years, there are plenty of chances to observe heavier particles by the Fermilab collider, Tevatron collider, and the Tsun LHC. Another impressive fact about the masses is that the second heaviest particle is the bottom quark, and the ratio of the square masses is 1/1400, which is order of magnitude of alpha over 4 pi. So if we're limiting ourselves to one loop calculation, which we are, then we can neglect all the masses of the quarks and leptons except that of top quark. In 1960, Professor Yang taught me the renormalization theory of quantum electrodynamics. Renormalization was carried out by Schrödinger, Dyson, Watt, Young and Mills, etc. Everyone here, every one of you must know the Young-Mills paper of the non-abelian gate theory, but you may or may not know the paper of Young-Mills that really have quantum electrodynamics renormalized, properly renormalized. Renormalization is an absolutely beautiful theory, but nevertheless, it leaves somewhat unpleasant aftertaste. Why should a quantum field theory have such divergences, which must be swept under the rug? Wouldn't it be better if there are no such divergences? Hopefully, the Fermi-Boson symmetry can help. Earlier papers of this type of consideration. In 1979, Ferrara, Girardello, and Parobo looked at this, and a couple of years later, Feldman did too. By the way, Girardello was my former postdoc. When their results are applied to a standard model, which is not clear they can be directly applied, we get the two formulas written there. They only differ by the coefficient of last term. Therefore, if we don't worry about the coefficient of last term, the coefficients are all the relation of a form, sum of the fermion mass square equals sum of the boson mass square, a relation which I find very attractive. If we apply their consideration to a standard model, there are actually two quadratic divergences. One comes from Higgs tadpole. Higgs tadpole means diagram with one external line, which is Higgs boson, and from Higgs self-energy, which means a diagram with two external lines, which are both Higgs bosons. To one loop, the cancellation of these of the two quadratic divergences, respectively, they're different, but they give the same condition on the masses. We do not really understand in a deep fashion why these two conditions are the same. But we want to apply this to our case. In what we're trying to do now, with the addition of these scalar quarks and the scalar leptons, there are now many more quadratic divergences. In fact, there are additional 24 of them. We would like to assume that all these 24 additional quadratic divergences all lead to the same condition. At first sight, this sounds like a very strong assumption, but it isn't, because these conditions all take the form of sum of fermion masses square equals sum of boson mass square. But as you have seen, for the fermions, there's only one heavy fermion, the top quark. Therefore, there's no way to write down a second relation that of the same form and still does not get into contradiction immediately. The calculation follows the method of that was developed in 1992. What was found, to our surprise, was the mass of the respective particles are almost the same for the scalar particles. For example, the UL tilde, CL tilde, and T tilde all have nearly the same mass. As I said, this is a surprise to us. Therefore, while we know the quarks and leptons form a hierarchy in masses in the three generations, the exactly opposite is true for the scalar quarks and scalar leptons. We find that quite nice. Now, let me give the result and then discuss the result. There are three features I want to talk about. For the scalar lepton, they are heavier than the scalar quarks, just opposite for the lepton and quarks. The mass of the right-handed scalar neutrino is small. That plays a role of the neutrinos in our own world. The other feature, which we'll have to get to, is the one at the bottom of the left-hand side, that the mass of right-handed scalar D is only 1/6 mc, which is about 15 GeV. We have to check whether there may be evidence already in Petra, Pep, or Trista against having such a particle, because they'll be pair produced by photon. This we have not done yet. So if there's evidence against such a particle, then the scenario will have to be modified. More accurate results for these masses will be obtained very soon using this approach. So now a few words about the decay. How scalar quarks and scalar lepton decay. The simplest possibility is scalar quark decay in the quark new fermion, and the scalar lepton goes into lepton plus the same new fermion. Therefore, the list of particles, the left-hand side are those we have, the right-hand side are new ones we want to add. There are numerous open questions besides the one connected with experimental observation of the right-handed scalar D. First, self-consistency. It's very strange because in all these derivational masses, the top quark mass is not used. Yet, the whole thing becomes non-self-consistent if the top quark mass were somewhat higher. If instead of 173 GeV, if we're 200 DeV, then we're already in trouble. So somehow, things are very tight. So now let me conclude. It is our hope, but emphasize it's only a hope, that the present consideration may lead to a new direction in the study of Yang-Mills gauge field theory. All quantum field theories in particle physics must be Yang-Mills gauge field theory. The standard model is an example. 2, Yang-Mills gauge theory and Higgs boson. We have already said the ratio of the Higgs decay mode to gamma from Atlas and CMS divided by the theoretical calculation with standard model is about 3. This implies new physics. Besides the top, there are other heavy particles that contribute to this loop. These additional heavy particles are likely to be spin zero particles, and therefore the Higgs boson is the first one of a family of spin zero elementary particles. The last slide. So the attractive possibility is that these new heavy spin zero elementary particles are scalar quarks and scalar leptons. This suggests possibly fermion-boson symmetry. Since symmetry dictates interaction, as Professor Yang emphasizes, the main question is, what does this fermion-boson symmetry imply about the interaction? In our scenario in the discussion, this fermion-boson symmetry implies a reduction of divergences in the Yang-Mills gauge theory. When I'm extremely optimistic, perhaps leading to a theory without any divergence. The first preliminary result from this scenario is a determination of the masses of 3 generations of scalar quarks and scalar leptons. Thank you.
Any question or remarks? David?
Yeah, I mean, if you were correct that the Higgs gamma process predicted by the standard
I'm sorry?
is 3 times the observed rate, it would be incredibly dramatic. But I gather that many papers have looked at your calculation and identified why it differs from the many previous calculations.
Yes.
Identifying the problem, your assumption
Yes.
that the Higgs to WW, Higgs to gamma vanishes, and the MW goes to zero limit, which isn't even true at tree level, where the Higgs can decay to W plus, W minus.
Well, Todorov and I have gone through many of these
I
papers.
understand. So you disagree with all of these authors?
Well, in every paper Todorov and I have gone through, we can easily identify what's wrong. But of course, we have not gone through all the paper. Which paper do you consider to be the most reliable
I was
one?
looking to
Huh?
refresh my memory at the paper by Schiffman, Weinstein et al., who identify where your assumption that the Higgs to gamma gamma or Higgs to WW contribution vanishes in the W mass goes to zero limit.
No, but this is the,
Because you work in unitary gauge, where there are 1 over MW longitudinal W bosons appearing in the loop,
yes?
gives a finite contribution in that limit.
But this,
And so there is clearly a disagreement, severe disagreement in the literature between your calculation and everyone else.
not everyone else. So far we know, this criticism does not apply to that of Christoph and Todorov. And so far I can understand the one of Christoph and Todorov is essentially rigorous, at least on physicist level. A mathematician probably won't be.
Paper I looked at was your paper
Yeah,
and Slayton's paper and
I'm sorry?
Gastman,
Yeah,
Wu.
yeah,
That paper gets this factor.
yeah. That's why I'm giving this talk only after the Christoph Todorov paper.
But you make an assumption
Huh?
or
Assumption.
someplace. You put in that the amplitude vanishes in the limit where the W mass goes to zero.
Well, that's a problem. That's a problem with Feynman diagram, which Christoph and Todorov did not have.
Okay, Monizi.
Yeah, I just like to change the topic slightly by just mentioning that several years ago, postdoc
I'm sorry, I cannot hear.
and later at Princeton wrote a paper in which we had this very simple model in which every clock has that case. So we call it private things, which of course some people don't know it for various reasons, but if you resolve this kind of stuff.
I'm sorry, I cannot hear.
Can you say a bit loud? PT cannot hear.
Okay, well, we'll talk about it later.
Okay. Okay, any other questions? If not, we thank the speaker again. Okay, Professor Yang have a question.
Yeah.
Crux of the problem is whether dimensional renormalization, dimensional method works for quadratically divergent diagrams. And Wu's paper 3 years ago could not be published because it differed. They made a straightforward calculation, and it differed from the canonically accepted calculation. So they cannot have their papers published. Instead, they then changed track and say that their calculation is correct, but and it disagrees with the experiment. So how should one amend that? And so they invented this new scenario, which is very peculiar. I'm not sure that this is correct. But the important thing is first to accept the controversy about what they did and what the generally accepted calculation did for the Higgs to 2 photon.
The generally accepted, this is a one-loop calculation. It can be done in Pauli-Villars. You do not need dimensional regularization. All the different calculations with different regulators give exactly the same result. It's a very standard calculation. And some of their assumptions are even wrong at the tree level. With their assumptions that the Higgs to W plus W minus would not appear when the mass of the W goes to 0. So even at the tree level, there's a disagreement. Regularization plays no role. You can do Pauli-Villars just as well at this one loop level. And in fact, some of the original calculations done back in the 70s were done with Pauli-Villars. It's like Ed Hooft, who first worked with, he didn't work with dimensional regularization, but one loop you don't really need it. Yes. So I don't think it's an issue of anything except they work in unitary gauge. In unitary gauge, there are terms which go like, the longitudinal particles go like 1 over mw. And those make a finite contribution when mw goes to 0, because 1 over mw cancels the other mw's. And they neglect that. If you put that back in, you get the standard result, which agrees dead on with experiment. And if they're right, there shouldn't have been a Nobel Prize for the Higgs mechanism because it's blatant disagreement with experiment.
Thank you. So we thank the speaker again.